See my title slide?
Yes, we can.
Yeah, thank you once again. So thank you, Dr. Varaprasad. You actually ended the right space. Of course, Varaprasad just sitting in the beside room. And before that, thank you to TechFusion, the organizers, Pura, Ramona, and all of you there. So as Dr. Varaprasad mentioned, today I would be talking about the digital twin modeling of an integrated transportation platform Digit project, because I won't be focusing on the digital twin part, but this is the project that we have with Middlesex University, TCS, IIIT Sri City, and IIIT Hyderabad. And the focus here, I'll go through what is the Digit project, but then we'll also focus to what I am working in our group per se. Here we are focusing on IoT-enabled V2X vehicular to anything platoon-like driving environment. I'll go through why I'm saying platoon-like. But before that, the Digit project overview, it's funded by UKRI and Spark, UKRI on the UK side, Spark mainly on the Indian side. The overview of this project is to build smart IoT vehicles. So that's the first part, which I look into aspect. The second is the communication between the heterogeneous vehicles and also understanding the environment through the drones, which Dr. Varaprasad is doing, and communication, of course, Dr. Ramona was involved there. The big data visual analytics and the digital twin modeling part, that again, data analytics, of course, we are doing to a certain extent, but then also with IIIT Hyderabad, and the digital twin modeling with IIIT Hyderabad and Dr. Varaprasad from Sri City and from Middlesex University. So, but before that, I'll just go on to a brief recap of what is V2X. I'm sure many of you know. We are looking basically at vehicle to anything communication mechanism, which includes a V2V, a vehicle to vehicle direct communication, typically within, say, if I'm looking at a DSRC, which is a dedicated short range communication, that would be around 300 or 250 to 300 meters. Then we have this vehicle to the infrastructure, vehicle to people, or vehicle to anything in the parking, and the overall vehicular to the networking environment, which would be mostly cellular based networking connected to 4G or the next generation 5G mechanisms. Just to give you a brief overview of what we are basically looking at from a big picture perspective, is that I have a base station, the next generation base station, and then I have several vehicles, cars, bikes, two-wheelers, autos, or three-wheelers here. And we want to have communication, as I showed in the previous slide, between different contexts, V2V, vehicle to the infrastructure, vehicle to networking, or infrastructure to the vehicle. Of course, here I want to focus on the vehicle to vehicle, as we are talking about in the Digit project as well. Yeah. So the Digit framework, we would be coming up with 4 layers in the Digit framework. The first layer is the communication layer, where we'll be demonstrating a real-time, seamless, and heterogeneous communication between different vehicles. And when I say different vehicles, it is different kinds of vehicles as well. So the idea is to have different cars, a two-wheeler, an auto, vehicles which have different communication capabilities, vehicles which come with different pricing. Why? Because some of these vehicles would be very low cost vehicles. So you probably cannot put the camera in all of these vehicles. But then use the mechanisms where some of the vehicles can capture the information and then tell the vehicles that are coming behind to unravel the information like traffic congestion, air quality monitoring, peak travel times, and then build in more additional intelligence onto it using machine learning and AI, so that we can analyze the data. And the overall idea is to create a digital twin of this entire vehicular communication network. So I'll just tell you briefly here what we are expecting to do as a final deliverable. We have in our own campus, a very less traffic environment, more like a racing track ellipse, where we are looking at having 3 to 4 different vehicles. As you can see, the vehicle that you see at the center is a IoT enabled electric bike actually. And then we are looking at making Segway. In fact, we are, as I'll show in the next few slides, we have been making IoT enabled Segway. And then we are looking at a totally different vehicle. I'm not going to focus on that. The idea is that all of these vehicles would be built here, built in India, or under the so-called Make in India scheme. But more importantly, from the electronics perspective, we are looking at putting a lot more IoT sensors in each of these vehicles. And the first vehicle would not only be IoT enabled, but the second and the third vehicles would be following the first vehicle. Of course, they would have its own obstacle detection and other gyroscopes and other sensors, which would eventually help in identifying the scenario. But then it would still be heavily borrowed by the information that has been captured by the first vehicle in the road. So the second and the third vehicle would be more like a platoon. That's why I mentioned a platoon-like environment, where it heavily borrows the information from the first vehicle, which should be transmitted wirelessly. We are looking at mostly a 4G or a Wi-Fi based environment. And the idea is to have a digital twin model in the command control center, which would not only first be a digital shadow, where it will not only capture the exact happening of these 3 vehicles in the command control center, but eventually control these 3 vehicles from the command control center. So the first part is to actually, we have an e-vehicle, and then we have our own device setup for this e-bike. So a device setup which we have developed ourselves here, which typically has the following components. We have the IMU sensors, camera, and the GPS. So IMU sensors typically gives you a lot more information like accelerometer, gyroscope readings. So all are inbuilt within the IMU sensors. Typically it can give up to 33 parameters. We are right now using 26 out of these 33 parameters. In fact, we expect that not all of the vehicles will have camera. Some of these vehicles only would have camera. So the vehicles which would capture the information would analyze and then pass the information to the other vehicles, which would probably have only the IMU sensors. Once we have this information, each of these vehicles would first do their own pre-processing. And since there are multiple sensors involved, we need to do a real-time sensor fusion mechanism and then apply the analysis using an AIML model. Computer vision, it would come if we have a camera along with the IMU sensors. Once we do that, we'd give these score, or we'd give a quantification mechanism, which would be then sent to the other vehicles behind on different parameters. I'm not going into that, which should be used by the second and the third vehicles and so on. So in this digit proposal, what we aim to do is that we will have 3 vehicles, wherein the first vehicle would send this information wirelessly to the second and the third vehicles, which would follow eventually the first vehicle as well. So just to show you what we have done so far, the first vehicle, the master vehicle, which is typically an e-bike, we have looked at the IMU data, which captures the accelerometer reading, magnetometer, gyroscope reading, and then we have used the GPS to get the exact location. So these are the tests that we have done within our own campus and just outside our campus within the Sri City, which is more or less like a planned business townships. The roads are much far better, so we can actually use it for testing. And then once we capture these camera data, we analyze the data and we identify few parameters like obstacles, potholes, any broken dividers, any presence of any other vehicle in the immediate neighborhood. and then pass this vehicle onto the second vehicle. So the next task would be to actually for us to look into the how the communication works between the first and the second and third vehicles, which would be what we are currently working with the other group members, including Dr. Varaprasad and the Middlesex University. But then what we have done so far in the last 4 months, apart from having the first vehicle and having a device set up which would capture the vehicle, we have built two vehicles, or we are finished with the building one Segway that we have built, which is a different kind of a two-wheelers, typically used for a campus-like environment. And then we are working on a little more rugged vehicle, mainly for climbing slopes, which I'm not going on to it. But what I want to focus a little bit is that we have actually built, we have actually designed first and then built an IoT-based self-balancing two-wheeler mechanism, which typically involves three components: the design, the mechanical part. We have actually done the simulation and then done the assembly of these vehicles. And then we are right now in the process of procuring. We have got some components. I'll just show you and integrate with the different electrical and the electronic components. The idea is that these vehicles would carry a payload of 80 to 90 kgs. So I have with me my team, the students who work with me. In fact, with the kind permission of the chair, I would actually request that my students who are here, they present these 2 minutes video and the explanation of making the segue.
So, good evening, everyone. I am Zahid from Indian Institute of Information Technology, Sri City.
I'm Karthik from IIIT Sri City.
Yeah, so let's I'll start the presentation of our segue video. So, okay, so yeah. So this is our IoT-based self-balancing two-wheeler or the Segway. And yeah, so coming to the overview, a Segway is a self-balancing personal transporter. It has a target payload capacity of 80 kgs. 36-volt BLDC hub motor is used with planetary gear system. So the advantage of going with the planetary gear system is it has a it is very compact, and also it has a high torque. So basically, which provides a better rider experience. Then 6-axis IMU ensures the PID algorithm works perfectly in maintaining an upright position while moving, and equipped with various sensors and camera helps in road quality analysis and pothole detection. So the various sensors that we are going to use would be, let's say, ultrasonic sensor, a proximity sensor, a GPS, and of course the IMU as well. So coming to the novelty in our Segway, yeah. So the state-of-the-art chassis design. So as you can see here, this is the top view of our internal chassis structure. So instead of going with a regular flat panel or a flat base, we have gone with a hexagonal rings. So this hexagonal rings in a honeycomb-like structure provides very high structural rigidity compared to the just a regular flat model of a flat chassis basis. So then along with that, we have used structurally enhanced side panels over here, and that high tension bottom support, which will make sure that a Segway doesn't bend when a payload increases, let's say beyond 80, let's say 90 kgs or 100 kg in that range. Then, so this is the front view. So chassis front view of the version 7.2. So, okay. So this is, we have come up with many different versions, each one being better than the previous version. And this is the front view of the version 7.2. So it has 2 wire slots on either side, a battery slot in the middle, and again, the bottom support, which will help in maintaining a perfectly straight chassis design. Then coming to the next part in our novelty is the collapsible shaft. So collapsible shaft basically increases the portability and makes it easier to store in like small and confined areas. So this is the extended view of a collapsible shaft, and this is the final collapsed view. So this will be on top of the Segway or the base of the chassis. So now coming to the overall design. so this is the overall view of the version 1. Version 1, okay, a very old version, the one which we initially started, and we have come up a long way from version 1, now currently in version 7. So we haven't mentioned this, the final view of the version 7, but we are working on it. We'll come with it soon. And then coming to our progress for this, I'll have Sharon speak here.
Yes, so the software we use for designing the CAD is called Fusion, and after we design the CAD from Fusion, we export that to a software called ANSYS, where we do the mechanical analysis. So first we tried going with I-beam support in the version 7.1, and as you can see, even with the I-beam, the bending is quite high, and to just reduce it, we tried with a different support. As you can see in version 7.2, we tried going with a new support system, which is called knee support, and this will reduce the bending, and even still, it's not perfectly straight. So we tried with a new support system, so which is the most recent one, and it's called the K pillar. So here this K support will focus on the load being distributed equally, so that the bending will be reduced, and we're still working on it to how to improve it so that the bending will be so less.
Okay, so after the mechanical analysis, the next task that we have performed is PCB design and its simulation. So what we have noticed is various different sensors in our IoT platform. So basically, like take for an example, IMU sensor, which is one of the most, not one of the most, it is the most important sensor in our whole design. So it works perfectly fine. Okay, it provides very accurate values and works perfectly fine at a constant voltage source. So which is why we are providing a voltage source of 3.3 volt and a 5 volt. So we basically design a PCB which provides both 5 volt and 3.3 volt at a output. So this is the 2D view of this PCB, and this is the 3D view of our PCB. So now coming to the SPICE simulation of these PCBs. Okay, so I'm not sure how well these graphs are visible because of this online mode, but as you can see here, the SPICE simulation, the current and voltage respectively. So we are getting a near perfect and perfectly regulated voltage, which is exactly needed for our requirement. So now the work that we have done in the electronics domain. So basically we created a 3D model of the IMU so that we'll have a better idea as to how this IMU or how this segue is moving as and when we move up and down the, let's say, slopes or up and down potholes. So we can basically better analyze the situation depending on various terrains. So this is the 3D model, and then with just a few different code snippets. So basically we have used both Kalman filter and complementary filter in our IMUs to increase to basically provide make the output as accurate as possible. So the complementary filter and the Kalman filter, and this is the code snippet that we have used for making the 3D model using Python. We have used various different Python libraries again. So now what's remaining? So finalizing the chassis design, we're making minor support to the bottom, the minor changes to the bottom support. So in the version 7.2, 7.3, just the bottom support has to be like made minor changes in it to make sure the bending is as least as possible. Then coming with the mechanical assembly, finishing the work in the electronic domain, basically controlling the BLDC motor, which is a whole different comes with a whole different set of problems. So controlling the BLDC motor efficiently so that our rider's user experience is better. And then finally enhancing the user experience by fine-tuning the PID control, because okay, so the segue, basically the main important function is the self-balancing part, right? So for that, the PID controller is one of the most important aspects of it. So fine-tuning the user experience, I mean enhancing the user experience by fine-tuning the PID controller. So thank you for your time, and now I'll hand it over to Hrishikesh, sir.
Yeah, so just a quick thing is that the Segway has been designed keeping in mind the fact that the roads mainly in the in a very nice campus like environment it would be smooth, but then when you go out of these campus like environment, a typical Indian or nation country roads or any hilly terrain roads, the roads are not necessarily very smooth and not always well maintained. Whereas the Segway has to still work, I mean, these platoon-like environment would be still be able to work in such an terrain and the road environment. In fact, we have gone for a patent of this design, filed the provisional patent there, and then in the process of filing the complete patent.
Yeah.
So the as I mentioned, we would be completing the building of these vehicle 2 and also the vehicle 3, which is in progress. I've not talked much on the vehicle 3 because again, that's we are looking at a different kind of vehicles which we would be patenting it or in the process of patenting it. But then the idea is to transform these vehicles into, of course, a smart vehicle and have the second and the third vehicle following the followers as an autonomous vehicle. And then as the project demands, we work with the other teams to establish the wireless communication link between the different vehicles, typically 3 vehicles to begin with, and then create finally a digital twin model for this array of vehicular communication network. With this, I end the presentation. So this is the team that are involved in this work. And of course, needless to say, we work closely with Dr. Varaprasad, the speaker who spoke before me and who introduced this project. And of course, with the Middlesex team, especially Dr. Purav and Dr. Ramona. Thank you.